Today, we're jumping into one of the most important ideas in the history of science, Niels Bohr's absolutely revolutionary model of the atom. Seriously, this was a model that saved physics from a paradox that threatened to break everything, and it kicked open the door to our modern quantum world. But let's kick things off with a pretty terrifying question, one that was seriously keeping the greatest physicists of the early 20th century up at night. You see, based on everything they knew about the laws of physics, the atoms that make up you, me, the chair you're sitting in, all of it, should have collapsed in less than a second. So, why are we still here?
To get to the answer, we first have to really dig into the problem. And that problem started with a brand new and what seemed like a brilliant picture of the atom.
Okay, so in 1911, this guy Ernest Rutherford does his famous gold foil experiment, and it completely changes the game. He figures out the atom isn't some plum pudding blob. No, it's got this tiny, dense, positive core, the nucleus, with these little lightweight electrons zipping around it just like planets orbiting the sun. It's a beautiful, elegant model, except for one tiny, universe-destroying problem. And this is where it all goes wrong. On one hand, you have Rutherford's nice, stable little solar system atom. But on the other hand, you have the rock-solid laws of classical physics, the same rules that predict how a baseball flies or how planets actually move. And those laws were screaming that any charged particle moving in a circle, like an electron, has to give off energy. And losing energy means it should spiral down into the nucleus in like a nanosecond. Poof, it was a death spiral. Physics was fundamentally broken. The situation was dire, and a desperate situation calls for a desperate measure. It needed a young physicist who was willing to just tear up the old rulebook and write a completely new one. And that physicist was Niels Bohr. In 1913, he didn't just try to patch the old laws. He came up with a radical new set of rules that, he proposed, only applied to the super weird world inside an atom. He basically said, what if the normal rules of the universe just stop working at this tiny scale? And these were his rules. First, he just declared that electrons can exist in special stationary states, where, for some reason, they just don't radiate energy. That's it. Problem solved. No more death spiral. Second, he said not just any old orbit is okay. Only very specific, discrete orbits are allowed. And third, an electron only gives off or sucks in energy, as a little packet of light, when it makes a quantum leap from one of those allowed orbits to another. Now, this idea of quantized orbits, this was the real game changer. Just think of a ladder. An electron can be on the first rung, or the second rung, or the third, but it can never, ever just float in between the rungs. Energy and position inside an atom weren't a smooth ramp you could slide up and down. They were a fixed set of stairs. Now, this all sounds like a pretty convenient trick, right? Just make up new rules to solve the problem. But Bohr's model was so much more than that. It was a predictive powerhouse, and it was about to solve a mystery that had been driving scientists crazy for decades. See, using his new rules, Bohr didn't just have a concept. He built a whole mathematical framework. He could now sit down and calculate the precise energy and the precise location for every single allowed orbit in the simplest atom of all, hydrogen. And the result was just stunningly precise. The energy of each one of those rungs on the ladder in a hydrogen atom was exactly equal to negative 13.6 electron volts. That's a super tiny unit of energy, divided by the orbit number, n squared. This wasn't a vague idea anymore. It was a specific, calculable number for every single energy level. He could even calculate the radius of the very first innermost orbit, what we now call the Bohr radius. And it wasn't some random distance. It was a fundamental constant of nature, about half an angstrom. All of a sudden, the atom had a defined structure and a predictable size. But here it is. Here's the mic drop moment. For years, scientists knew that if you heat up hydrogen gas, it doesn't just glow with a continuous rainbow of light. It only emits light at very specific, sharp, colored lines. And nobody knew why. Well, Bohr's calculations for the energy released when an electron jumped between his quantized orbits, they predicted the exact position of every single one of those spectral lines. It was a perfect match. The mystery was solved. This was the proof. The Bohr model was an absolute triumph, a home run. But as it usually goes in science, it wasn't the final word. It was, instead, a flawed masterpiece. I mean, its successes were just monumental. It gave us the whole concept of quantized energy levels. It completely nailed hydrogen spectrum, and it laid the groundwork for technologies we use every day, like lasers. And to this day, it's still the first way we introduce the quantum world to students. But the model had some pretty big limits. As soon as you tried to apply it to an atom with even one more electron, like helium, the math just fell apart. It didn't work. It couldn't explain some of the finer details in the light spectra, and it totally missed a fundamental, super weird truth we discovered later, that electrons also behave like waves, not just little particles. So, if the model was ultimately wrong, what's its real legacy? Why is it so important? Well, its legacy is that it was the first, and arguably the most important leap into a whole new reality. You have to think of the Bohr model as the critical bridge. It's what got us from the comfortable, predictable world of classical physics to the bizarre, probabilistic world of quantum mechanics. It forced physicists, kicking and screaming, to accept the strange, quantized nature of the subatomic world, and that paved the way for the even weirder and more accurate theory we use today. And here's where that bridge led. We went from Bohr's simple, almost comforting planetary model with its neat fixed orbits to our modern view. Today we know electrons exist in these fuzzy probability clouds called orbitals. We can't actually say where an electron is, only where it is most likely to be. Bohr's model got us thinking in that weird quantum way, even if it didn't have the final, complete picture. So while it was simple, and ultimately flawed, the Bohr atom represents something truly profound. It was that crucial first step. You could say it was the moment humanity first glimpsed the quantum nature of reality. And for that, it remains one of the greatest leaps in the history of human thought.